We have an example problem here. A 50-volt potential difference is maintained across a 2-meter length wire that has a diameter of 0.5 millimeters. If the wire is made of material that has a resistivity of 7 times 10 to the negative 8 ohm meters, what is the current in the wire? So being given a resistivity and some dimensions of the wire, that should lead us to think about solving for resistance. And if there's resistance, then the current flow is going to depend on the potential difference applied across this wire divided by the resistance. Well, whether we substitute Rn symbolically first or solve for R and plug in doesn't necessarily matter. Let's go ahead and find R and then find I. So the resistivity is that rho value in our equation. L is the length, which we're told is 2 meters long. A is a cross-sectional area. Since they give us a diameter, that implies a circular cross-sectional area. Oh dear, sorry. Area is pi r squared. So pi r squared, where r is the radius. Since we're given the diameter, we need half of that, and we will square it. Okay, I'm getting 0.713. The units on this are ohms. I forgot to write my meters in here on R in the denominator. When we take this meters, we've squared it. It's going to cancel with these other 2 meters in the numerator and leave us with just these ohms. So 0.713 is not a very big number. This would not be a very large resistance at all. To find the current that would flow through it, we take the potential difference that's applied across it and divide by this resistor value, or resistance value, I should say. $70. And that's rounded to 2 sig figs because that's what we've been given in the problem. That's a lot of current. But it's a lot of current because this is a very small resistance. Now, technically, all wires, even wires running from our outlet to our light bulbs, all wires have some resistance, but ideally a very, very small amount. As we solve problems both in this chapter as well as the next, we're going to assume our ideal wires, or that our wires are ideal, meaning we're going to assume the wires that connect, say, to a light bulb. We're going to say that the resistance is 0 in the actual wires, and all of the resistance is in the light bulb. Which may or may not be a bad assumption. It depends upon how big your resistor values are in your circuit. But this is just to simplify things for us. If we follow that path like we did with the capacitor, around from one side of the battery to the next, if the light bulb is the only thing that we're accounting as having resistance, then the light bulb is going to end up with the entire battery voltage across it. By saying the wires have no resistance, we're saying the connecting wires have no potential difference. Now, granted, depending upon how long the wires are and cross-sectional area, all that good stuff, there is going to be some resistance in a real circuit.